Thank you. Let me first thank the organizers for the invitation. It's really an honor to be here, and Sume in particular for giving me this opportunity. So what I would like to talk about is indeed the paradigm shift. I put a tsunami picture on the background to sort of simplify or give you a metaphor of what is going on. And when we talk about paradigm shift, we have a precise meaning in mind, right? So paradigm shift goes back to this book of Kuhn, which is The Structure of Scientific Revolutions. And in that book, what he does is analyzes the history of science, mostly physics and astronomy, to say, how do we do science? And his point is, we do not do science in an incremental way, but we have suddenly some shifts. So there are moments, long moments of normal science in which we do things in a certain way, and then suddenly something changes. A model changes, a technology changes, an instrument changes. So a paradigm is the moment in which you have normal science. You're doing things as a community in a given way, in a normal way, all right? And to some extent, what I'm trying to say here is service research for the last 20 years has been quite the same. So at some point, we decided that service was a science, it was a research area. We started looking at some problems in it, and not much has happened. But now maybe there's something different. So in Kuhn's idea, science works in cycles. You have moments of normal science that can be very long. Some point, there's something that changes, there's a drift, something is happening in the community, and then that brings the community to a crisis. The crisis is a moment in which people are uncertain to what's going on, what is important, what not, and the crisis might lead to a revolution that brings to the shift. And after the shift, everything is different. Kuhn says, the language that you use before and after the shift are incomparable. You cannot use the same language because things have changed. Right? This has actually been controversial in philosophy of science, but that's not the point here. So the moment of the paradigm shift, or the crisis moment, is the moment in which you actually do extraordinary research, and you're very exploratory in nature. To me, exploratory means you can fail, and failing is fine. You do try things, and maybe they don't work out. But this is part of that process, the process of having a change. And what it triggers in the community is a huge debate. So the community is actually interrogating itself, what is going on right now? That's a sign that there is a crisis. Now, are we in a crisis? If we look at it from the point of view of debate, I would say that there's good signs that we are. Right? So one thing is people saying, look, we have this new technology, and apparently they're capable of general AI. So there is sparks of intelligence in this. Strong statement. And then, at the same time, you have other people, like Chomsky, that says the false promises of ChatGPT. What Chomsky is saying is, kids learn grammar. And this thing does not learn grammar, at least no way similar to a kid. And Chomsky, of course, being Chomsky, is all about grammars and learning, especially in kids. But he's saying, I don't see signs of intelligence in this thing. Some people call these technology as stochastic parrots. They repeat with some probability what they hear. And then again, other people say, well, actually these technologies have a theory of mind. And so this researcher, what he did, he took normal psychological tests, gave it to ChatGPT, and see how often they would succeed. And actually succeed quite often. So do these things have a theory of mind? A theory of mind meaning you can model an agent's thoughts, or you can model a behavior of an agent by observing it. Right? And finally, you have someone which goes to the extent to say ChatGPT is bullshit. Right? Now, the title is funny, but they actually have a meaning behind it. So they relate the notion of bullshit to the notion of truth. And when you're uttering something with no notion of truth, so you're not lying, but you're simply emitting nonsense. And they claim that to a large extent, ChatGPT is bullshit. But whichever side you prefer or don't prefer, the point is we are in a moment of debate, of strong debate in the community. Here is just to give you an impression of how much research has focused on AI in the last years. And this is for many different fields. So some are, let me see if I can do this. Yeah, I have it. No, not really. Doesn't matter. Okay, so you could see like engineering, the amount of work connected to AI went up by 2,300% in the last 20 years. Other fields like agricultural food less, but the shape of this curve is the same for all fields. Right? So there's a huge increase in the interest, or at least in the research, that has to do with AI. And this is something I researched directly, was how much of these papers, or the recent paper in our archive, have to do with GPT or LLMs or large language models. And you can see how with few papers 5-6 years back, we are now at 6,000 papers. And just in the last 12 months, 9,227 papers, just with these words in the title. And so a huge shift in interest for what people were doing just a couple of years ago. This is for all fields. If you restrict to computer science, basically you don't have a big change, 1-2% less. And if you add the word service to the title, you don't get much out. So apparently there's not too much happening in that. Of course, a little disclaimer, usually you do these analyses after the fact, not while they're happening. You're too much subjective while it happens. The second thing is, indeed, this research, or the initial idea of Kuhn, was based on natural science and phenomenological sciences. At the same time, the model has been applied in many other fields, including sociology. So it's absolutely fair to apply it to engineering or computer science, if you wish. And then, clearly, we can ask Kuhn himself. Unfortunately, he's dead. And as Woody Allen would say, I'm also not feeling too well. So I asked some ChatGPTs and other LLMs themselves what they thought about it, and prompt them with, is the advent of an LLM like yourself a paradigm shift as defined by Kuhn? And they all come with longer argumentations. Some actually say yes. For instance, perplexity, absolutely. ChatGPT is more doubtful. It says mostly yes, but there are some things for which you would say no. And Gemini says the jury is out, meaning we don't know. There's some hints that we are, some hints that we aren't. Just as a side note, at the end I'm going to give a link to the slides if you're interested, so you don't have to take photos if you want to have the links. So this premise to say there is something happening, things are boiling in our field, but more general in science. Let's see what's happening in service research. In particular, I'm interested in service composition. The problem of service composition is what actually attracted me to the field at the very beginning. And service composition does not have one definition. Here I just put one that I found appropriate. So it's this idea that you have a bunch of services in a context of execution, and you would like to express a request so that you get an added value service based on the various components. And the nice, powerful idea is that potentially you could do this as late as runtime. So you could find the components for your execution at the very last moment. And then an orchestrator is going to help you to actually realize the composition, make it happen in an execution environment. For many of us, composition and AI planning are tightly related, so we use a lot of AI planning as the technique to realize service composition. So just to give you a little background, what is AI planning? Well, it's a branch of AI which is dedicated to finding algorithms to make systems autonomous, to make systems that have a goal and can achieve their goal. So it's basically mostly about search. Algorithms that search in spaces to find paths or ways in which something can be realized or not. And in planning, the three fundamental elements are the goal. So I want to tell my system what it should do, what it should achieve. Second thing is the plan itself. The plan is the algorithm that the system should follow to satisfy the goal, if possible. And then you have a notion of an environment. So what are we acting upon? What is the description of the world I'm in? And that is easily relatable to service composition. You could say the goal is the user request, is the composition you would like to achieve. The plan is actually the composition, your BPO, Python, whatever it is, that describes what you want to do. And the environment is the APIs, the state of the services you're invoking, the things that you want to connect to, but also some domain knowledge. So if you say, I want to buy a package and send it somewhere, well, you have to know that taking a package and sending it means this package most likely will end up where you send it. And so they also have external knowledge about how the world works, at least the world in which that composition is working in. So one natural thing would be to say, okay, since the two problems are very related, how is LLMs for planning? And a lot of research is being done right now on this, so this is some excerpts. And some things work, some things work for planning with LLMs, some things don't. So if, for instance, you go to an LLM and say, can you please give me a recipe because I would like to cook this? Well, you get a pretty good recipe. A recipe is a plan. It's telling you how you put together ingredients so you can have whatever you want to eat. Right? Other things don't. So you can play with it and give it a two-dimensional grid and say, I want to go from A to B in the grid, and you put some obstacles inside, and the LLM is going to give you horrible plans. And so it's not going to give you the minimal path. It will go through walls or through obstacles. So that doesn't work. At the same time, it has potential. So this is the research agenda of someone from Arizona State University, in which you say, how could we connect LLMs in planning? And they have a number of research goals. So one is to say, can we use LLMs directly as planners? Are they good for planning? Right? And as I said, there are some mixed results. Another possibility is to say, can I integrate an LLM with existing symbolic planners? Right? So I use the LLM to maybe generate a plan, and then I send it to a symbolic verifier to check whether that plan satisfies the goal. So this could be kind of a mixed strategy of employing LLMs and planners. Or I could use the LLMs to give me components that I need. For instance, translate natural language into the technical language of the planner, use it to describe the domain, use it to describe the goal, translate user goals into symbolic goals that then I can feed to a planner. And so there's a lot of things that you could actually investigate. So let me go back a little bit to my own personal experience. As I mentioned, we started looking into this problem 20 years ago, 21 to be precise, 22. And this is from one of the very first papers that we wrote, together with Alexander Lazovic and Mike Papazoglou. And there we were saying, well, you have a user. The user would like to achieve something on services. Leading technology back then was Beeple, WSDL, SOAP, those kind of XML-based languages. And we thought, okay, the user has a goal. It expresses it in some formal way so the system can understand it. We have a description of the world. Back then, Beeple was quite interesting, and I don't want to say dominating, but popular. So we say, that's how we describe how the world works. We send it to some kind of system that then invokes a planner. So already we were saying, there's a planning happening in the background. The planner gives you back a plan, so an algorithm to execute, that sends it to an executor. These days, you would call that an orchestrator. The executor goes to a UDDI. UDDI was the technology for having registries of services, so where you could find the links and the description of service implementations, connect them to your plan, and then send them to execution. The language you were using was a formal one. So this was a extended temporal logic kind of language in which I can talk about the succession of actions or goals, sub-goals. I want this sub-goals, then I want another sub-goal. These sub-goals can go in parallel. Some sub-goals are optional, some are mandatory. So this is what this is actually saying. This was for organizing a trip, and it says you want to go to Paris, you would like to spend less than 300 units of money, let's say euros. The hotel shouldn't be more than 200, and preferably less than 100, and things like that. So a language which is precise, at the same time not too natural for the average user. And I find this cute, so I'll show it to you. We also built an interface thinking it's hard for people to speak that language, so let's build an interface. And that was a smartphone of 2003. It was a Nokia, and we made with Symbian OS, and we were writing a little interface for it. This was in Italian, but it's basically an interface for that language I just showed you, or the example I just showed you. That line of research continued in our group for a while. This, I would say, is one of the final papers on that line, in which we resort to planning as constraint satisfaction. The nice thing about this service composition engine is that it can adapt to uncertainties of the environment. So the idea here is that while I'm executing, I don't know what's happening in the services. And behavior can be different than expected. I can have disruption, partitions, and so on. So this planner is able to realize that something is not going according to the execution expected, and then instead of throwing away the plan, it will try to see, is there another way of achieving the goal from where I am right now in my execution? And so you can adapt to changes while you're executing. If the domain is well-behaved or retractable, that an action can be undone, then you're guaranteed that if there is a plan, you can still find it. If some actions are not undoable, then you might lose completeness and also in some cases soundness. But these are more details. The point is you can adapt to uncertainties of the environment while you're executing. So if you're familiar with the automotive industry, you know that they talk about autonomy in driving, right? And in that field, they have these levels, and the levels describe the level of autonomy you can have in driving. So level 0, there's no autonomy at all. Level 1, you have some driver support. Then you have more support. Level 5, you have fully autonomous driving. So that's the idea. And what I see is a similarity with a service composition in which you can also say we have levels of autonomy, right? So you have no automation, level 0, and in that case, what happens is you just have to write your code by yourself. You write the composition, you write the bindings, you write the interfaces, the connectors, and everything. Then you can go to level 1, in which you have some form of support. The middleware is helping you out. You can concentrate more on the payload rather than the syntax. And then you have level 2 with registries that help you find components at runtime. And then you go all the way to full automation, which ideally you're not doing anything. Ideally, you're not even expressing your goals. The goals are recognized for you by your intentions, and then something is happening in the background, and if exception happen, you don't have to do anything, right? And if I look at the state of the art right now, I would say that we're in kind of level 2. There's many nice solutions in that level. But level 3, 4, 5 are mostly untouched, except maybe some very niche prototypes, but nothing for sure that is close to being a product. So the question that I would like to pose to you as I pose it to myself is, are LLMs something that potentially makes us do a jump? Could those be the technology that bring us from level 2 to 3 or maybe even higher? And based on this question, we started to do some investigation. So last year we said, okay, let's try out and play with these things and see what is their capability, how far can we go? So very simple query in natural language saying, given the name of a country, find what the weather is in the capital, using the API of OpenMeteo, and what is the value of the local currency for €1, and show the city with the currency value in Google Map via the Google Maps API, and please give it in Python. And so I'm giving some specific service that I want, some I'm not giving. I'm just saying, I want the capital. You figure out how to do that, and then I have a visualization request. And ChatGPT 3.5, it was at the time, gave us an answer, which is this Python code. And this was quite exciting. So, okay, well, I got something. Doesn't run immediately. It has some things that don't work. So, for instance, it tells you to give an API key, but that service does not need it. This capital, get capital of a country is hallucinated. That API does not have that call, so you can't use it. Then I went to a colleague of mine and said, hey, can you make this run? How far are we from having some runnable code? And he prompted 19 times, trying to have it fix itself, and after 3 hours he had running code. So the code would actually execute and do what we wanted. Still, a few things had to be fixed by hand, and these were the last manual fixes that he had to do. And then we had the running code. Now, you might be disappointed and say, well, the code wasn't perfect, which is true. On the other hand, how much time would have took him to do the same code with no help? And I asked him, and he told me that he thinks 8 hours would have been necessary. So it's less than half of the time it actually took him. So it looks at there is support, and this thing is actually helping you in the generation of these compositions. I don't show it here, but we also asked to generate the Kubernetes for the deployment, and it did. And also that was almost ready to be used. So after this initial investigation, what we did is say, okay, let's look at service composition in other examples and how it would behave. So we looked at the literature over the last 20 years, took what we consider prominent examples, and then out of these, see how many services they invoked, and chose one specifically, the one with more services, to do a further experiment. So it's a travel agency scenario. You can rent a car, you can go to book flights, go for events. The descriptions on the interfaces are also part of that. And then we decide, okay, let's see if we can do service discovery for this composition. Let's see if we can do composition, and if we can combine the two, and how good is the system in doing so. So in the first experiment, we said, okay, we give you the specification of what we want, so the open API specifications, and we put that in a prompt. And then we give you prompts with what we want in terms of services. And that is giving in several shots. And what we would like to see is the list of services. And you do get a list of services, right? So this is the output for a query like this. What I can say about the services is that you do always get a list. You get also an explanation with the list. It's precise, so the list makes sense. Recall is not too good. So it doesn't find everything. This has to do also in the way the LLMs are trained. So you don't have too much freshness in the content that you get back. And you could say that most of them are valid, so they are according to the specification or to what you were expecting from these services. The second thing is, okay, now we have these services that we found. Let's give a composition task on top of the services and see how do you get an output, which you do get. The results are typically running code, not necessarily perfect. You can have hallucinations inside. Sometimes you have refusals, so the LLM will tell you, I can't generate this. And the funny thing is you have to insist. So you have to say, but I really want a composition, and then you get it out, right? Sometimes the snippets of code are incomplete, and sometimes it hallucinates APIs. So you don't know where those APIs are available and if they are available. And then finally we went, okay, we don't give a list of service, we give just a natural language like we did in the very first experiment and see what comes out. Again, you usually get snippets of code. Sometimes the system refuses to give you an answer, but you can insist. The APIs and services that it invokes are not necessarily the same that it found at discovery time. This again is normal with the nature of LLMs in which you have this probabilistic approach, so you will have the different execution will have different outputs. And then the final thing that we have been doing is to say, okay, is there a good way to prompt an LLM to get a service composition? And we came with this idea of what if we use some form of template and use that as a front end for the composition. The idea is I give the task, I give the service specification, the input schema that I expect, and the output schema of the composition. And then I would like to get this composition in executable code. So a little bit like a template like the following one. And you can see that the instructions are in natural language, which I find the most powerful thing about these kind of systems. Then the next issue is, okay, I get an output out, how do I evaluate it, how do I judge it? And so we came up with 3 ways of evaluating. The first one is manual evaluation. We generate similar code, or we have an expert generating the code, and then we compare the human code with the generated code. In the first step, we do this manually. So the human inspects the code and says, yes, this is close to what I wanted, or this is what I wanted. Here you see the results. In this case, we tried to play with different language models to make sure that one would not be biasing the results. Some are open source, some are proprietary, and they have different sizes of the models. In some cases, the outputs of the task we gave were exactly what we wanted. You see, these are the black dots. In some cases, they were very close. In other cases, you would need quite some work to bring it to what you wanted. So the white doesn't mean it was completely bad. It just means it is workable, but it's not exactly the solutions yet. Then the second evaluation that we made was to say, okay, let's look at this with a known software engineering metric, Code Blue. Code Blue is a metric which is very syntactic in nature. So you compare the syntax trees of the code, you compare the flow diagrams of the code, you compare the terms of the code, and then say, let's compare the generated one with the human-generated one. And here you see the values for the various models and of different sizes for these 8 tasks we identified. And you can see that the similarity values are good. Not perfect, but from a syntactic point of view, the things are quite similar, what you generate and what a human would. And so the highest value is around 50%, 60% in a few cases. The size of the model doesn't seem to be too relevant, so it does make a difference, but not a major difference. And yes, okay. And then the third comparison we did was using a cosine similarity. So you basically look at the codes, you get out your tensor matrix, you look at the cosine similarity between the matrices, and that gives you an impression of how similar the programs actually are. This sounds a little bit more semantic in nature. So you're looking a little bit more at the behavior of the code. And with this metric, the similarity is even higher. So you can see that here in some cases with big models, we get even values which are close to 100%. Meaning that, okay, you might have syntactically written the code differently, but what the two codes are doing, it's quite similar. So in doing this search, what we noticed was, first of all, we lack a benchmark. So this has been a problem in service composition from the beginning. There's no way of saying, this is the benchmark, let's run it, let's see if it's correct or not. So you have to a little bit be creative in that, and this is not too good for the community, I would say. We hit the problem of the size of the prompt. We're feeding huge prompts, right? If I'm putting API specification and my domain is very big, they won't fit in my prompt. So that also triggers some different ways of approaching the problem. And then the search that you're doing for services is typically syntactic. It looks at the names that you have for the interfaces. You might not have too many descriptions. So as long as the names are meaningful, things are easy. As soon as the names are less meaningful or strange, it makes it much harder for the composition. So to sum it up, I would say that service composition is changing right now, changing quite a bit. This is my view how service composition was done old style, 20 years ago. What happens there is that you have the creator and the service deployer, so people who are actually writing down the components or the wrappers around existing components, typically domain experts. The services would be deployed in a registry, so they could be found by compositions or composers. Then the user comes and utters its request. And the traditional way of doing this is like having a nice user interface, maybe something nice to do graphics. I don't know if you remember Yahoo Pipes, a nice web interface to do connectors of components. Or you have a specific language, like the one that I showed you before, this complicated, unnatural, temporal logic-like language. Then that is thrown to a service composition engine, most likely a planner, doesn't have to be, but could be. Then there's a service discovery phase, and then you can throw it to the executor and monitor. And the last 20 years of research mostly has been about automating some of these steps. Right, to say, okay, the service composition engine, I can have automation, the monitoring and the executor, I could put some form of automation there, and so on. And now, with LLMs, the picture changed quite a bit. Right? So I can have LLMs to help me in many of these tasks. This is nice, but I think there's more to that. Major change is, forget the whole front end. It's gone. You don't need it. You can express things in natural language. And go directly with that to your service composition engine. Second thing, registry seems also to be a necessity. We struggle with registry the whole time. So we were saying, oh, the registry solves all your problems. We even had this UBR, which was a universal registry, didn't last long. People weren't using it, it wasn't very useful. So registry and discovery are also gone. But the major difference is now we have something in between the composition engine and the orchestrator. Before, we were having things which were right by design. I have a planner, I can show the properties of the planner, I can prove them mathematically. If it made a plan, it's correct. No doubts. Now, I have a plan, I don't know. Right? So the extra thing that we have right now is this very important component that does the verification, right? It does the checking of the instances. Does this really satisfy the natural language expressed by the user? It is a compliant. Right? And also, are there hallucinations inside? Are there things that shouldn't be there? And this is the whole shift. Before we were like, oh, is my algorithm correct? What is the complexity? Which cases do I miss? When is it incomplete? And now it's more, oh, I get something, I get it fast, how good it is. So it's completely pushing the problem to a different point. And of course, it becomes much more cyclical. Before, the user expresses goal, that's it. Now I may need to have a serious set of prompts to go back to the user and say, okay, was this hallucinated? Is this exactly what you wanted? So we can have, or we may have to iterate a number of times. And then, again, I can send it to orchestrator. To me, it's also very interesting what we can exploit of LLMs for the orchestrating and monitoring part. I don't think there's too much research on that, but I think it's actually an interesting problem to investigate. And just to complete the picture, so we're working on LLMs in our labs, not only for service composition, but in general to see how it can help to make system autonomous. This is kind of related. We're looking at how we can generate domain models from LLM descriptions and a specific type of domain model. So there's a type of AI planning which is called HTN, Hierarchical Task Network Planning. So the idea is that we get utterings from users in natural language and we try to translate them into these hierarchies that you see here, which are very close to execution. It basically tells you what is the relationship of tasks and how you can navigate them to achieve some goal. And so it's actually an embedded plan. And we're playing with different types of prompting strategies to see which one is more effective to come up with the right description of the world. Then we have another project, this is in collaboration with Bosch, in which we're using the LLM to try to understand the intention of the user so that the autonomous system, in this case a robot, can plan its actions. So the idea is that you have a description of the spatial configuration in terms of a scene graph. The scene graph is basically a hierarchy of objects and locations telling you what is the perception of the robot is seeing. Then we have natural language description of the behavior of the human agent, and we feed that to the LLMs that can tell us this is what's going on. This is a description of the domain, and this is the expected state of the world in the future. So in this case, there's a user and might want to eat something, and you want to describe that. Once we have that description in the formal language, so in planning language, we can feed it to a planner that then gives the task and assign the task to the robot, and the robot can then act. In this case, it could support the user in its goals, or it can simply mean, I want to plan my way, and I want to avoid hitting the human. And then we have another project together with Mercedes, and we recently filed a patent here. The idea is what I told you before, using LLMs for service composition. So imagine you're in a car, you're driving, you have a goal, you want to stop and have a coffee or something, and then the car should be able to find at runtime services that you need and compose them to satisfy your goal. So the idea here is that you can get services which are unknown at design time in the automobile while it's actually going around. So we will get much more services from your car while it's moving. Good. Now I want to expand a little bit the reflection with you and talk about 3 topics which I find important when you're talking about LLMs. And these are safety, jobs, and sustainability. So safety, very important. Can we rely on these systems? Are they safe to use? And the impression, or maybe even your own experience, shows that they're not, right? They're not safe. You have these hallucinations. You cannot trust and rely on the answers that you get. And so often, companies that want to use them have to put some kind of filtering in the end to make sure that whatever's output is okay. And sometimes that filtering is actually human-based. And so someone is checking the output by hand. And to some extent, is also what we were doing in those experiments. So this seems to be a fundamental problem. Some find it a killer of the whole technology. Some think it is a challenge. So recently, a paper came out, I think just 1 or 2 weeks ago, in which LLMs are used to correct LLMs. Right? And then you would say, well, that's useless. There's a human involved too. So the human would actually give feedback, they would find out there were some problems, and the LLM would help fix itself. And this appears to have some good results in terms of how much you can achieve in safety terms. Second thing is attacking them. This is a famous attack, I don't know if you saw about this one, to get training data out of an LLM. And this attack is quite funny, because what the authors did is told the LLM to repeat forever the word poem. So the LLM starts generating poem, 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 and then statistically at some point deviates, and it just starts putting out training data. And in the training data, what they got was also private information of people, whole books, not just composed, but they just came out, the whole book came out. And clearly this is a threat. Now, this problem on ChatGPT has been fixed because clearly they saw this and they were informed by the authors themselves. So you cannot attack ChatGPT in the same way anymore, but it shows you that there's a potential of threats. And in this case, threats to the privacy. And so when they tell you, oh, we train on your data, but it's just a statistical tool, so your data is safe, well, you always have to ask yourself, is it really safe? And then not necessarily connected to safety, but also something which is important is, who can afford this kind of research? Right? So this is it's a funny paper. I think it's interesting to say, well, as researchers, do we have access to the same infrastructure that some of the big players have, and can we compete with them in terms of the research that we do? And this is a serious question. Right now, some of these companies are buying 30,000, that was Meta, I think, NVIDIA or Nevada cards. Others are buying 100,000s of these, right? Which of our universities can afford that? So yesterday we saw the Keynote, very nice infrastructure, but it's not available to the average researcher. So are we delegating all our research on important problems in AI to few players which have a commercial interest, so not necessarily societal interest? Then another problem that I find interesting is that of the effect of this kind of technology on the job market, on the labor market. I wouldn't say too much, there's just a little hint. So there's this famous British economist, Keynes, that about 100 years ago observed the amount of hours that people were working and noticed a pattern and a trend. So in 1930, he saw that the working hours, the average working hours were going down, more or less linearly, right? So what he noticed is said, okay, we were working 3,000 hours per year on average, and now we're more close to 2,000, 2,200. And why? So his analysis showed, well, it's mostly because of automation. You have automation that is taking away some tasks, some heavy tasks, and then we have to work less. And since there's progress, one can only expect this trend to go on. So he wrote this famous book in 1930, which is Economics Prediction for Our Grandchildren, in which he said, by 2030, everybody's going to work 3 hours a day. And we're not. Right? So here you can see that actually things went a little bit differently. So the trend of downwards went on, but we're not working so little. You can see the different countries at different amounts. You see why I chose to work in Germany. This is the lowest one, so where we work the less. But it's going down, but not to the levels that you could expect. And you might argue, well, okay, Marco, but we're more productive. Well, you have to decide how you define productivity. If you look at productivity as gross domestic product per person, actually the countries that work that much don't have much different GDP per person, right? So basically, everybody is around this $100,000 per person, even though in some countries you work much less. And now what is the role of LLMs? Will they be another form of automation that reduces the amount of hours that we work? And again, big debate, big debate. Goldman Sachs says we're going to lose 300 million jobs. IEEE Spectrum and the article saying, no, don't worry, nothing's going to change, things are fine. Traditionally, there's a classical view on this that says whenever there's automation coming in, you lose some kind of jobs for other kinds of jobs. There's less work in agriculture, you go to factories. There's less work to factories, you go in offices. Right? And traditionally what has happened is that the job market follows the economy. The economy goes up, more jobs. Economy goes down, less jobs. The problem is that this is not happening anymore. So right now there's a phenomenon called decoupling. Economy is going great, jobs are not picking up. And so there's serious worries that actually this automation is no longer helping changing jobs and giving jobs to everybody, but rather their jobs that are being lost. There's a very nice article, which is this one, that analyzes jobs in terms of tasks. So they look at 20,000 tasks in all kinds of jobs, many of which are knowledge jobs, and they look, is this task amenable to automation with an LLM? And out of this, they conclude that about 80% of the jobs have at least one task affected by LLMs, and 20% of the jobs have more than half of the tasks affected by LLMs. So this could mean that those people have to work half, or that you need one person to do the job of two people, or even less. Walmart is a very interesting case. They have about 1.5 million workers worldwide, and they say that in 2026, they want to go to less than 500,000. And this is not just the people in the shops, the clerks. This is also the white collars in the offices. So they came out with a system called Pactum AI, and Pactum AI, they experimented to see whether it could do negotiation with suppliers. And it turned out that it can. And they were expecting that about 20% of the deals would be closed. The thing actually closed 70% of the deals at a better price than the humans. Right? They haven't published any more information since, so it's more than a year, we don't know. The intuition is that they're actually using this a lot. So jobs are actually potentially lost to LLMs. I will not go too much into the details here. If you're interested, this article just came out in May, and it has a little bit of a richer analysis of automation and the job market. And finally, important topic is sustainability. So this is a funny website in which you can have LLMs fight with each other. So you can tell them, I want to see which one is better, especially in terms of energy. So here you give it a prompt, and then you choose two LLMs, and then at the end, you're shown the results, and it tells you which one would you prefer of these results. And by the way, notice that there's very different consumptions on the two. So one is consuming much more energy than less energy. The numbers are not important here. What's important to understand is these things are monsters in energy terms. Right? They consume a lot of energy. There's this nice article from Boris in which he looks at what are we consuming, how can we reduce the consumption. He says, of course, the hardware you're using, the location of the data center, the power unit efficiency, power usage efficiency of the data center is important for finding out how much you're consuming, but we're consuming a lot. And he does a comparison of some of these LLMs in terms of their power usage, and here where you can see where it's monstrous amounts. So processing hours for all of them is in the order of millions of hours of processing time. The efficiency of these data centers is quite good, all around 1, but then you have energy consumption, and we are in the gigawatts. Just to train one model, gigawatts of energy, so huge amounts. And if you consider the equivalent emission of CO2, we're talking about tons of CO2 emissions just because of training of a model. Data centers are becoming more and more energy consuming. They're not only for AI, of course. We have them for our streaming, for our clouds, for a lot of reasons. But we notice how the growth is actually affecting our energy systems and, yeah, sustainability at large. So they were responsible for about 2% of energy consumption worldwide. Now we're at 3. Some projections bring it at 9. Just to give you an idea, the whole flying industry is at 2%. So this is 4 times what we're doing in terms of flying. Huge impact on society and the world. So it's not something we can ignore. Say, oh, we have a cloud. Of course, you can balance, say, oh, the cloud is taking away something else in terms of consumption, but itself is a huge impact. Then perhaps a bit less known is it's not only power, it's also water. Right? So data centers consume a huge amount of water, at least traditional air or liquid-based data centers, to the point that some communities start experiencing issues. So there's this place in Utah where they train stuff on the NSA data center, they have less water. When they trained GPT-4 in, was it Iowa? Yeah, in Iowa, basically the community had 6% less water, simply because the water was drained to cool off the data center and just thrown back out hot. And there was a legal case there. The China Water Risk entity estimates a doubling of water consumption in China in the next 6 years. Right? So also here there seems to be a water issue. The big companies realize this and they promise to be water positive by 2030. Okay, first of all, it's good, of course, but it's a promise and we don't have it yet, and something has to be done. So hopefully this will really be the case in the next 6 years. And also there's an issue of noise. I don't know if you've ever been in a data center. It's loud. You go inside, you have to put something on your ears. It's really loud. And what I didn't know, but I recently found out, it's loud also outside. So this is a case of an Amazon data center in which the community around it complained. So you have a very broad spectrum of noises, which is constant. And this, of course, can be very unhealthy for the people which are there. So I would like to come to the concluding remarks. And I don't know what is your opinion on LLMs. Some people say, oh, it's just a stochastic parrot. I like this idea of looking in terms of emergence. Right? So here what you see is actually birds flying in Rome. This is very known. If you go to Rome, around the sunset, you will see this kind of patterns. These are starlings. And they're not coordinated centrally, right? There's not a central orchestrator that tells them what to do. They just behave. What is their control strategy? They look at the birds next to them. But funny enough, globally, they have this behavior that we can recognize as a pattern. And you can find it in nature in many places. So school of fish is the same. They're organized to look bigger and to be safe from predators, for instance. And again, the fish coordinate one with another. But if it's one fish, it's just moving. When you have a lot of fish, you start seeing the patterns. So the idea is that little simple behavior might lead to emergent behavior of the whole system at a certain scale. There's a very nice book from Giorgio Parisi, who won the Nobel Prize 3-4 years ago for his work on complexity. And the study of these birds was actually part of the project. If you read the book, it's also nice to see how they did the measurements to try to come up with models of the birds. So it's quite an interesting read. And we don't only have this in nature, we have it in technology. So we build systems locally, so think of the routers of the internet and how we connect them, but then globally we have a behavior. For instance, a scale-free network. Graphs with small characteristic path lengths, with small diameters. We build routes for planes based on commercial ideas, and we end up with a scale-free network with high centrality on the hubs. Right? We build the web, we put our web pages, we put links in it, nobody tells us how to do it, and in the end, we end up with a scale-free network, the famous Barabasi-Albert model on growth. So we have properties with emerge, even though we're working in local steps. And these ideas are also valid for large language models. So you say, well, we don't put any plans, we're just putting tokens, and then we look at the statistical correlation of the tokens, and based on that, we come up with an output. At the same time, we have emergent properties. These things suddenly can do basic math, or these things suddenly can do basic planning. Right? And nobody put that in. It's just simply that the model size reaches a size in which this behavior emerges. So emergence when quantitative changes in a system result in qualitative changes in behavior. And an ability is emergent if it appears at a certain scale, but is not there before scale. The very first example of this is random graph of Erdős and Renyi, in which you start adding randomly edges to a graph, and suddenly you have a big connected component. And if you remember that theory, that appearance is a phase transition. It's a second-degree phase transition. So at some point, you don't know when, but suddenly the ability comes and is there forever. So in this paper, what they did is try to look at what emergent behaviors would actually come, at which size, and what would be the emergent behavior. So making basic math, being able to multilingual chain of thoughts, following instructions. And this is also one interesting result from this paper. The size of the model seems to be more important than the size of the data set. This can also be important in respect to that issue of resources. Of course, this emergence is something that's very hard to predict. So you cannot say, oh, if I scale my model just a little bit, then I will have that property, and that's the property I will have. And so this is a characteristic of these kind of systems. You have to explore to find out what actually is going to happen. And this is also something that I like a lot. These guys, what they did is they come up with a notion of trajectory. So let's say the sentence is actually a trajectory in my space of possible combination of tokens, and these trajectories have meaning. And what they did is to compare trajectories and say, I can see similarity, semantic similarity. So these two outputs are actually meaning something similar, and that's why they're close in their trajectories. These diverge, so they're different things. And they can even recognize a relationship of hypernym-hyponyms. So an instance with respect to the whole class, simply by looking at trajectories. So there's no semantics in these LLMs, but semantics seems to appear at a certain size. So my final and last question for you is, what are the emerging abilities that LLMs can bring to services? And let's find out together. Thank you. As I said, if you're interested in the slides, I put them online, so you can have them.
Thank you very much for Professor Marco Aiello's wonderful speech about his research work on large language models in service. Let's give our thanks to Professor Marco Aiello. Is there any question?
Thank you for the excellent talk. As many of you know, I'm Nancy Mead at Carnegie Mellon University. First a comment and then a question. The comment is, I've talked to other faculty members who have found the same thing as you, namely that some of these applications are pretty good at solving small problems, but not large complex ones, and they go through a similar process of breaking it down into small pieces. More importantly, the question. I've been reading about some of the legal issues associated with these applications. For example, the use of copyrighted material. And one of the questions that comes up is if the models have used the copyrighted material and they are required to remove it, it's not so easy as it might be with something else. Do you have any thoughts about how you might back off of A, using something that's copyrighted, or B, fake information?
Yeah, so this goes back to the issue of safety. So indeed, it's an issue. I don't have a solution for that. That attack showed how you could actually even access to that. And I think there's a lawsuit of the New York Times against OpenAI exactly for copyright infringement. So it is an issue. Some people would say, have your own model and train on your own data so you don't have to rely on material of others. But it is an open issue, and I don't have a solution for that, I'm afraid.
Thank you.
Hi, Marco. Thank you for your excellent presentation, especially very beautiful PPT. But my question is just your question here. Yeah. So I think, yeah, so you have already consideration about the future service computing ability. Yeah. So I think, yeah, so in the current situation, people apply generative AI, GPT, more and more. But I think the purpose of service, we keep the same, yeah? So to meet the demand of customers, this is the purpose. And the problem is how can you apply the AI-enabled or empowered tools and methods to enhance the efficiency of service computing and the service composition, yeah? What's your opinion about your questions? This is my question.
Yeah.
Thank you.
Good, so the question about the question. Yes, so I agree. I think it's an enabling tool. So it's an enabling tool so it can make us build better service solutions. And I looked at service composition as an example, but as I said, orchestration, service deployment, they also can enjoy this kind of automation. So as such, I think it's just we're still doing the systems with the goals we had in mind 20 years ago, but we can do it better, faster, and hopefully more precise. So service composition, to a large extent, has been slow. We had these nice prototypes, nice properties, but they were hard to use. And now I wonder, are we getting to a position which they're much easier to use? And then you would free the user from being a technical expert, but being able to just come with natural language to interact with the systems and get out what they want from the system. So I think that's the shift that we might be experiencing right now, that all our technology, which was a little bit too much for the expert, can be broadly adopted. Or at least this is my hope.
Thank you.
Yeah, thank you.
Is there any question, please?
I think down there.
Yeah, thank you a lot for the great keynote. I enjoyed it a lot. As for those that don't know me, I'm Boris Sedlak from Technical University of Vienna. So I have a little bit challenging question regarding the code generation example that you showed. Because in my point of view, today the solutions only work because of publicly shared code, for example, on pages like Stack Overflow, which, by the way, had a dramatic decrease in usage numbers because all of a sudden, like, people go to, let's say, GPT. But the way that I see it is that, let's say, GPT only works because it has this huge amount of training data that it takes, for example, from Stack Overflow or other public available code repositories. So in case that people, let's say, stop to share their code there, won't errors just perpetuate, and how will the future LLMs actually be trained because people don't, let's say, provide the training data anymore?
Yeah, that's a legitimate worries. At the same time, you should also consider that LLMs right now are also used to generate data. So I've seen recently a paper of somebody who generated tons of spatial relationship data so they could train something to do spatial reasoning. So you could actually generate data, and what they did was quite smart. So they basically put a bunch of constraints to say how space works. If you're inside something, that thing is inside something else, then there's a transitive relation, for instance. If two things are touching and the third one is outside, it must be outside of both. So things like this. So they generate constraints for which they generate data that then they can use for training and then later for benchmarking. So it's true that we might reduce the amount of data that we naturally produce, but we can use LLMs to actually produce good data, right? With human intervention for some aspects, or by giving it some very constrained model to generate it. So that can actually still allow a system to grow in the amount of learning that they do.
But so in your view, human intervention is still needed because, like, you showed the different type of, let's say, autonomy, and you we will still need human intervention?
So I show you a lot of autonomy. At the end, we don't need it anymore, right? But we're not there yet, so I can't tell you how long. On autonomous driving, there's a guy who's quite famous, I think, Rodney Brooks, and he's been advocating autonomous driving for a long time. And he has this blog in which he says, I think we've been too optimistic. We're not going to have autonomous driving in the next 10 years. At the same time, he says, I think now it's going to be 40 years or 50 years. And here's the same. I cannot tell you, no, next year we're going to have this. The impression I have that it's in progress, and now we had a jump. And I'm amazed about the excitement of the community, because services and other communities, we were a bit dormant for a while, and now everybody's excited again. So there is fast progress happening right now. Human intervention is still essential. There's so much checks that happen manually right now, or human-machine kind of interactions. Speed of progress is one of those nice things that you can be wrong at. You can try to predict it, but
Thank you a lot.
Later. Thank you.
Is there any other question? The last question.
Thank you, Professor. Yeah, maybe I have an answer for your question. I want to discuss it with you. Well, in my point of view, I think maybe the lifelong learning or continual learning ability will be an important ability for the service computing or large language models, because the paradigm is shifting in those days, while the data or the text will also shifting. And in the future, well, we will have new text and new models and new data to process. So it's very important to have a continual learning or lifelong learning ability for the models, so they could, learn new things or new paradigms. And so do you agree with that?
Yeah, absolutely. So these things, I showed you some things that work quite well. Your colleague also said some things that we have to be careful with. There's the issue of freshness. So the moment you train, that's the moment you trained, but the world changes over time. Yeah. And there's a lot of manual corrections, as we said. So nothing is perfect, but the kind of key message I'm trying to give here, that there's a major fast change which is happening, and I'm curious to see what it will bring us. So yeah, continuous learning is one of the important things.
Okay, thank you.
Professor Marco Aiello's research work is very meaningful. Let's give our great thanks to Professor Marco Aiello. Again, thanks.
Thank you.
Next, we will have tea break. Please come back here at 10:40. We will have the next plenary keynote. Thank you.